Throughout the universe, the behavior of energy is regular and predictable. According to the first law of thermodynamics, energy is constant, although it may change from one form to another form over and over again. Energy in the form of heat flows from one place to another by conduction, convection, and radiation. But the net energy flow goes only in one direction. Hot things tend to cool off, cold things tend to warm up, and an egg once broken can never be reassembled. These examples illustrates the second law of thermodynamics, one of the most fascinating and powerful ideas in thermodynamics. The second law of thermodynamics places restrictions on the ways heat and other forms of energy can be transferred and used to do work. In here, we explore three statements of this law. The first and the most intuitive statement of the second law of thermodynamics is that heat does not flow spontaneously from a cold body to a hot body. The second statement of the second law of thermodynamics is that you cannot construct an engine that does nothing but convert heat completely to useful work. The third statement of the second law of thermodynamics is that every isolated system becomes disordered with time. Although these three statements appear to be very different, they are actually equivalent. Given any one statement of the second law of thermodynamics, you can derive either of the other two as a consequence. For example, given the statement that heat flows only from hot to cold objects, a physicist can produce a set of mathematical steps that show that no engine can convert heat to work with 100% efficiency, which is another way of saying the second statement. In this sense, the three statements of the second law of thermodynamics all say the same thing. The first statement of the second law of thermodynamics refers to the relative temperature of two objects. If you take an ice cream outside on a hot summer afternoon, it melts. Heat flows from the warm atmosphere to the cold ice cream and causes its temperature to rise above the melting point. By the same token, if you take a cup of hot tea outside on a cold day, it cools as heat energy flows from the cup to the surroundings. From the point of view of energy conservation, there is no reason why energy should necessarily work this way. Energy would be conserved if thermal energy stayed put, or even if heat flowed from an ice cream to the warm atmosphere, making the ice cream colder than it was at the beginning. Our experience and many experimental confirmation convinces us that heat flows spontaneously in one direction, from hot to cold. It does not go the other way on its own. The second statement of the second law of thermodynamics restricts the way we use energy. If we recall the definition of energy, it is the ability to do work. This second statement of the second law tells us that whenever energy is transformed from heat to some other type of energy, from heat to electric energy for example, the energy is neither lost nor destroyed, but it can be used to make electricity to play your radio or fuels to drive your car. Physicists and engineers use the term efficiency to quantify the percentage of useful energy an engine can deliver. Efficiency is the amount of work you get from an engine divided by the amount of energy you put into it. In equation, E is equal to T hot minus T cold divided by T hot times 100%. Consider the efficiency of a normal coal-fired generating plant. The temperature of the high-energy steam, the hot reservoir, is about 550 kelvins, while the temperature of the air into which waste heat must be dumped, the low-temperature reservoir, is around room temperature or 300 kelvins. The maximum possible efficiency of such a plant is given by the second law, as efficiency in percent is equal to T hot minus T cold divided by T hot times 100. 550 minus 300 divided by 550 times 100 is equal to 45.5%. In other words, more than half of the energy produced in a typical coal-burning power plant must be dumped into the atmosphere as a waste heat. The third statement of the second law of thermodynamics that every isolated system becomes disordered with time is in many ways the most profound. It tells us something about the order of the universe itself. Consequently, This idea of increasing disorder in the universe is perhaps the most familiar way of looking at the second law of thermodynamics. To understand the third statement of the second law of thermodynamics, you must understand what a physicist means by the term order and disorder. An ordered system is one in which objects are positioned in a completely regular and predictable pattern. For example, automobiles in a perfect line are highly ordered systems. A disordered system, on the other hand, contains objects that are randomly situated without any obvious pattern. Automobiles after a multi-car pile-up on the freeway is a good example of disordered system. To illustrate the phenomenon of increasing disorder, let us use food coloring and water. Plop a drop of food color into a jar of water. Gradually, the molecules of the food coloring disperse through the water. The same thing is true of perfume or cologne. You put it on in the morning and by evening, it's all gone, dispersed into the air. Entropy is a measure of the disorder in a physical system. The entropy of an isolated system remains constant or increases. The example of food coloring and water reveals how such a process works. In the most likely situation, when molecules of water and food coloring are randomly mixed, the entropy is maximized. In the much less probable case of food coloring molecules coalescing in the water, the entropy is lower because the molecules are more ordered. Another way of saying this is that systems tend to avoid these states of high improbability. While systems tend to become more disordered, the second law does not require every system to approach a state of lower order. Think about water, a substance of high disorder because water molecules are arranged at random. If you put water into a freezer, it becomes an ice cube, a much more ordered state in which water molecules have formed a regular crystalline structure. By placing water in the freezer, you have caused a system to evolve to a state of higher order.